Yeah.
So let us start our
Sure.
seminar today, and we welcome Professor Rita Fioresi from University of Bologna. She worked on multiple disciplines across algebra, geometry, physics, and machine learning. Today, she will give a talk on geometric deep learning with quantum groups. So please, Rita.
Yes. So first of all, I thank her for the very nice invitation. And as I was saying right before the seminar, I regret not being present, but that was due to some personal issue combined with a very busy schedule as far as trip are concerned. But be assured, I really want to come there. This will happen and will happen soon. So now the talk, it's very strange to see two different topics meeting. And the reason why I give this talk is based on some research that I started back in 2017 regarding the possibility of merging machine learning models with what I know of mathematics. The reason being that if you read the paper of the people writing, these new machine learning tools, you see immediately that these people have a very limited knowledge of mathematical instruments and they cannot really do mathematics. I say it with the utmost respect because they're doing great things, except that they don't have strong mathematical modeling. So I started looking into it, and the more I look, the more I see the need for such mathematical modeling. So I started asking for grants, and then I got three grants: Calista, Caligula, and California. And Calista is a collaborating grant that Professor Van Lee is also participating at, and any one of you can participate and ask for money. And to be honest, we need help to spend it. So you guys should write me an email, say, how do I participate? How do I spend the money? And I will be explaining to you. There is some competition, but I welcome the high standard thing. So here is a little bit more information regarding the Calista grant. It has 5 working group, and there is, you see, and if for me it is like has any topic for everybody because it has Cartan geometry representation theory, which is my background, and then integral systems and supersymmetry, which is some physical application, non-commutative geometry, quantum homogeneous space, and then the working group 4 is vision algorithm. That is the deep learning part of this talk we will see. Not really fully vision. We will talk about more how can I say, more structured neural networks. We will see in a moment. And then the dissemination and public engagement. So again, if you want to know more, just write me email and I will explain to you and point you how to join. Finally, one last thing, and then we start with the mathematics. I want to say that with Paola Schieri, we got another one of these grants. So it'll be starting very soon, and it's called Magic. And with Professor Van Lee, we applied for another one. So what I'm trying to say is that more money may be coming my way. So I'm really glad if you guys, people interested, participate with me. I see Peter is here. Right, Peter, congratulations to all of us for the new Magic grant that we just got. So this should be a great, what can I say, encouragement for everyone to apply, right? Aren't we happy, Peter, that we got it? I feel very, very happy. So it's right.
Ciao, Rita. Me too. So
Great. So,
yeah.
and everyone should apply because the truth is that with Paolo, we're not expert in machine learning. We are expert in mathematics that want to model machine learning. And that's the message from this talk that you receive from me. There is a lot of mathematics that is unexplored and unemployed and should be employed in machine learning. So in this talk, I purposely do not assume any knowledge of machine learning, and I will try to explain from the very bottom what is this mathematics amounting to. Is it okay, Hong, if I do like that, like try to explain also some bit of machine learning because I want the things to merge nicely, right? So I can safely assume that you guys know very little about machine learning. Am I right? That would be a correct assumption, right? What do you say? Is it okay? I don't want to bore the people. So there are a lot of like neural network works that concern graphs. And here we see the graph of a Facebook. So this is a very composite graph because, as you know, the nodes may be of very different type. For example, you see right here, there are the nodes are people, and they may be linked with the notion of friendship, but other nodes are substantially different. So, for example, other nodes can be, you know, things that you like to do, like Netflix or, for example, cooking. So there is the need in a graph to understand links and nodes differently. Okay, so these are very strange type of graphs, and right now. The way we see it, the people in machine learning are not fully comprehending the mathematics behind it. So the way they look at it, they just put a graph with different nodes, and we believe we can do better. Now, in quantum geometry, if you look at the beautiful book by Majid, there is the idea of what is quantum differential calculus. I will explain what that is. And this is springing directly from the need of physics to understand gravity and gauge theories on lattices and graphs. So that was the motivation of Majid. So they're writing all of these operators like, I don't know, all these differential operators on graphs and on lattices because they have this physical purpose. When I was reading this work, I was thinking that, well, they developed it for physics, fine, but the people in machine learning are not aware at all of these ideas. Moreover, not only differential operators are needed, but as you know, in geometry, the concept of sheaf plays a very big role. Why? Because you can think about the sheaf of differentiable functions. It can capture, you know, what is a sheaf. For the sheaf of differentiable function, it will take an open set in a manifold and give you back the functions on that open set. So when you do this assignment, you are capturing not just what happens at a point, but you're capturing what happens in the neighborhood of a point. So this is particularly useful for the graph I represent there, because you don't want to know only what happens at this person, but you want to capture what happens in the nodes. For example, this node is a friend, so you just don't want to know what are the preferences of the person, but you want to know the preferences of the friends. So this makes it very useful, the idea of sheaf. And in fact, the machine learning people have developed the theory of sheaf neural networks, but not knowing geometry fully, they developed it in a way that I will try to explain. It is not fully mathematically. So to give a little bit of a spoiler, what they have developed is the so-called flat case. So they assume that the graph is a manifold, but is a flat one. Why we think with my research group that writing neural network with curvature may enhance the power of the network. But this is like the bottom line of this talk, just to tell you where we are heading. So guys, so far so good. What do you say? It's a small. Okay.
Yes.
All right. Okay. So let me try to put some mathematics. I don't want to what can I say, frighten the people in the sense that there is a lot of categories and in the very technical stuff, and I want to keep it very mild because I don't want to here express my mathematical theorem. But today, what I want to do is to see there is a bridge between these very abstract notions and very concrete questions. So let us look at the category of ordered set. So with n elements and for every n, and then the category of ordered sets where we just fix the number of elements, okay? Then the functors that associate to this object a set, then, functor going from the category of such object to sets, is called a semi-simplicial set. This is something that is well known in algebraic topology. Certainly, we are not inventing anything. We're just borrowing this terminology. Why? Because we want to treat not just graphs, but directed graphs. It will be clear that the notion of directed graph is very important. At the moment, one does not understand why, because things, the machine learning people operate with just graphs, not directed graphs, but the direction has a strong importance in this point of view. So just to see a very important example, you can see the semi-simplicial set of dimension 1. It has two objects, the 0 and 1. And then the 0 is associated as set. So it's associated this set G0, so that's a factor. And I call this set the set of vertices. And then to the object 1, you associate another object, which I call the set of edges. And then the factorial property of G will force the existence of two maps that we call head and tail, that essentially will tell you what is the vertex, which is the edge, and what is the vertex that is the tail of a given edge. Okay, so you have head and tail of an edge. So far, so good. You may think, and you'll be right, saying, why, Rita, do you view a graph in such a complicated way? Because a graph is a set of vertices and edges. So you could do without this complicated picture. However, you have to trust me. This picture will allow us to understand it in a more profound and factorial way, so that the constructions will be more natural. Moreover, if you just look at a graph, you have that the edges are a subset of VG times VG, meaning that typically in the theory of graph, you allow one edge between two vertices. Why? On the other hand, you may think to be more general and wanting more than one edge. So the reason, there are several reasons to do directed graphs in this more conceptual way. Okay, then we can put a topology on graph. I spare you the fact you can do it very factorially using the concept of Grothendieck topology and sites, and that is what we do in our paper. But let's be very modest here because I want to communicate ideas and applications. So you can define the partially ordered set structure on a graph, which is I take x less or equal to y if x is equal to y, or it is a vertex of the edge y. Okay, so this is an order, but is a partial order. Great. Then you can define what is called Alexandrov topology on this, that coincides with this open set around a vertex, which is the star of all edges, and by taking the edge without vertices. Clearly, you could decide, and this is a matter of convention, to look at the dual topology and take as open and close just vertices and edges. Now, these open sets are irreducible and form a basis for this topology. Now, this is a very strange phenomenon occurring here. This topology is profoundly different from the topology we are used to, the continuous function topology on manifolds and so on, because you have open sets that you cannot shrink. So these are irreducible. There is no other open sets contained into them. This makes the whole theory a bit awkward and marks an enormous difference with the continuous case. So what happens in the machine learning papers, what the people do, they look at the continuous case and they try to mimic it by looking at the discrete as an approximation. You see, they try to approximate for, the number of vertices and edges going to infinity. They try to approximate a manifold. But this is very wrong because they have a very profoundly different topology. So you have to consider discrete from the very beginning. And in fact, if you start considering this point of view, you see that many constructions that they do in a very unnatural way become natural. And you can push them further, things that they cannot do because they try to mimic, so that sometimes they get lost, obviously. And in fact, the theory of shift neural networks just stopped they did it only in a couple of papers, but people were not pursuing it because they're not understanding the fundamental issues connected with sheaves that require a bit more than just knowing the definition. Okay, now there is a key result that you can find in Grothendieck EGA, so the basic reference for the theory of sheaves and schemes. If you take a topological space, and this topological space has a basis that consists of irreducible open sets, then you have an equivalence between pre-sheaves and sheaves. And this equivalence is obtained by doing the sheafification of the sheaf. And it works beautifully because what happens is that you just essentially extend it uniquely. So this is a very functorial construction. As you can totally see, is this equivalence, it's like you can, of course, do it for the continuous case, but it is not true. So there are no irreducible open sets there. So you cannot play the but you can always extend the sheaf, except that the extension is a bit more complicated. Here is much simpler because of this irreducibility. So once you understand that it's enough to have a pre-sheaf, and pre-sheaf is just something very simple. You take an open set and you associate a ring of functions. That is, I'm sorry, I didn't recall the definition. I apologize it, but I said it for a differentiable manifold. Well, for any object, geometric object, a sheaf, when you have a topology, you take an open on this object and you associate a ring of functions in that has nice properties, so they will restrict nicely to subsets. Now, once you understand that is enough to specify the functions on the irreducible open set, so remember that these are the only two things you care about, this E, the edge, and this star, right? So if you know function on that, you can extend the function everywhere else. So what does it mean to have a sheaf of vector spaces on a given digraph? Well, it means that you need to give me a vector space for each vertex, and you give me a vector space for each edge. But that's not enough. Why? Because, as I said, I want the maps that you produce to restrict nicely. Now, the only possible restriction, because these open sets are very elementary, is that you can restrict in these stars, right, every edge to the vertex belonging to that edge, right? So let me show you. So if you have, so for this edge, if you give me a function on this edge, you are giving me a function, period. But if you want to give me a function on this star, you have to make sure that this function restricts nicely on this edge. So essentially, you are not free to give me whatever you want. If you want to give me a function on the whole graph, you give me on each edge, you give me on these stars, making sure that on each edge, the function agrees. Okay? Now, this thing, even they could understand, because of course the machine learning people don't understand the sheaf theory, but they understand what I just said, right? I mean, this makes very much sense. So, since they don't know sheaf theory, they take this as their definition of sheaf, which is very confusing from us for two reasons. First of all, that's not a sheaf, right? Well, it is because of the key result, but the way you give it to me is not apparent that is a sheaf. And in fact, they call it they call it with the name cellular sheaf, because it is a sheaf on an ordered set. So you need an order, a partial order, and then you can give this definition of sheaf. Beware that this is the theory of cellular sheaves is like a sheaf on simplicial complexes is quite nice in mathematics. I mean, it has been developed, and it's continuous counterpart is no less than the theory of perverse sheaves, right? Which are technically not sheaves. But this is a different story. But just to tell you that these are highly non-trivial mathematical objects, okay? Even though the application is quite straightforward. And then they also look at the dual topology. Okay, fine. We know that it makes no difference to look at the dual topology, except, just take close what it is open and that. So far, so good. How do we feel about this? Happy?
Rita, I have a lot of questions, but maybe that
Please.
is I don't know how should maybe that it start from the beginning, from my understanding. That is
Yes.
machine learning, and in particular, neural network is about the model of prediction in presence of the incomplete information. Do you agree?
I am sorry, I didn't
I
understand.
mean, that's
It's
first you
about?
have to begin is the definition, and you say about the graph and topology and sheet theory. So, geometric deep learning, of course, that's important here is the learning and then deep and the geometry. Yeah. So, what is the learning here? Learning here is
Okay, yes. So, no, you are right. I purposefully did not speak about that, but I am happy about answering this question. So let me go back to this type of question. So in a graph like this, you may want to answer to some questions, okay?
yeah. So, what you
So
want to learn? What is the model of incomplete information?
exactly. That's very good. That's exactly. I was going to make a concrete example. So, for example, you have a person and you have the connections which are labeled, and then suddenly you're looking at this node and you see there is a link. And what you want to predict is that is this node a friend? Is this node a like? Is this node a network? So, you want to give what is called the node prediction. So you want to predict the label that you put on the node, okay? For example, this
So
node is,
yeah.
yes,
So like sorry for interrupt, but of course that is how to say. Neural networks usually have kind of traditional networks such as modern usual function. So that is a deterministic function, but it's some modern of incomplete deformation of information. And then Bayesian neural network is incomplete information modeling is in sense of Bayesian static. And what I think what you're saying is that the last type of neural network is a graph neural network. And that only specific
yes,
for very small part of the, how to say, prediction model. So what you say is a graph neural network, right? And note that
yes,
because on this, how to say, ChatGPT, Gemini is a basic mostly on the traditional neural network and the Bayesian neural network. And what is
yes. So yes, I'm speaking only a graph neural network. And
right?
in particular, today I will speak only about how you can move the information from node to the neighboring ones. So
Yes,
this, because today I figure we are among mathematicians mostly, and you guys want to know the mathematical modeling of diffusion of information inside a
sure.
graph neural network.
Yes.
That was
So of
the
course that's
focus.
important, but that is more like yes, um, yes, part of the graph neural network. I agree. So thank you. So let
Yes, yes.
continue.
So I purposefully did not speak about the general. I just wanted to show how to diffuse information. And moreover, I don't speak about training or stuff. I just speak about what is called, if somebody knows convolutional neural network, this is operation which is convolution
Sure.
that will look into the neighbor of some point of the network. And here in graphs, the convolution takes place of this, what is called the message passing. And
Sure.
today it's only about that. So I
Yes. So yeah.
ignore
So
everything
mostly like
else.
discrete mathematics, right?
Yes, that's why I focus on one mathematical aspect. But
Right.
I thought that today was people would be
Yes.
interested. But thank you for the insight. Perhaps next time I say more about the machine learning because
Okay. Thanks.
okay.
Yes.
All right. So now what happens here, what happens here is that in our paper, we realize that the usual topology that you put on graphs, this Alexandrov, sometimes it is not sufficient, but you need to do something called étale. If you know étale in algebraic geometry, fine. If you don't know étale, don't worry about it. We don't need people to know the theory of descent. Absolutely not. But we are inspired by it. So what is the idea here? We are trying to take a graph that has many edges, like this one, and we're trying to cover it with, graphs that are, in some sense, standard. They will have just one edge per vertex. What we pay with it is that, of course, instead of having just one vertex, we need all three vertices here. They will be collapse. They will collapse in the vertex V. And similarly on the other side, we have a vertex W1, it will collapse in one. You can always do that. You don't need certainly a theorem to say that. I mean, it's kind of obvious. And you can define Grothendieck topology and étale coverings, okay? So you could give the notion of sheaf in a more general way, because if you do know what a Grothendieck topology is, you know that there is the theory of sites and topos exactly thought to give this notion. And in fact, this is what we do. But for today's talk, let me just tell you that we have a way to define a more general topology covering in some sense what you have. What is the advantage for it? The advantage is that you know differential calculus on H1, H2, H3, and you want to transfer the machinery to G, which is more complicated. That is the reason why you want to do this thing. But you want to do it in a mathematically sound way, and that's what we do. Now here, I again try to motivate the reason why you would do such a thing, okay? The reason being that in this picture that I took from a machine learning paper, you see clearly that you have the same vertex Zi that receive different type of information from different nodes. So you need a mechanism that somehow collapses the information coming from different sources. We saw similar example also in the previous case when there was the Facebook example. So what I'm trying to say is that the usual theory of graphs can help, but it's not enough. You need to be more general in order to diffuse the information correctly. That is, so this is an example of étale topology where you collapse the information, the vertices. Okay, now we come to, geometry deep learning meet quantum geometry. Now we come to the quantum geometry. So I spoke about various techniques on graphs for machine learning. Now I come to the non-commutative geometric part. So in non-commutative geometry, what we do, especially in the theory of quantum groups, we try to extract key information from some structure, geometric structure, in order to give a non-commutative version of it. And that is the case of first order differential calculus. You fix some algebra A, okay, and you have a gamma and D, you call it first order differential calculus, when your gamma is a bimodule with respect to A, and you have a K-linear map, K generally is a field, that satisfy the Leibniz rule. Everything is a K module, of course. And then you want some subjectivity notion. That's regards the fact it is connected. But the last property is important, but not so much for us. The typical example of a first order differential calculus, the one has to keep in mind, is when you take A to be the algebra of C infinity functions on a differentiable manifold, and gamma as the one forms on this manifold. then your differential d is just the normal exterior derivative that you are very familiar with. So I'm just saying that in ordinary geometry, this is what you would do. Well, in quantum groups theory, we know very well that the situation is way richer, that you may have several different first order calculus on the same object, even in the case of groups, even when you ask by covariance, which is an extra property which I don't talk about, meaning that the situation is richer. And for graphs, this is also the case. If you try to define first order differential calculus on graphs, you see that you have different choices. There is this work by Dimakis and the work by Majid, but also by Aschieri, Castellani, and collaborators. They worked on the differential calculus on graphs, on finite sets. Again, for physics. So let us briefly look at what this differential calculus amounts to. So you take the algebra on, on a finite set. This is spanned by the Dirac delta. That is not, what can I say, not surprising. So delta x are the functions that are, 1 on the vertex x and 0 otherwise. And I think I don't have to convince anybody that this is really the algebra of functions. And then you define first order differential calculus. This is one possibility, but you could do others. I don't want to enter into the classification, which I personally don't even know that well. You have to give me a bimodule. So the bimodule is the span on the edges. And then you have to give me a bimodule structure, where you give it simply by saying that when you take a function and you multiply it by an edge, this is the value on the left, it is the value on the head, on the tail, while if you multiply it on the right, it is the value on the tail. And then you look at df as this sum. And if you know something about, singular homology, you see this is really the operator D of singular homology in this special case. So you can define this D on generators exactly the way I say. Now, the interesting part is that this first order differential calculus is inner, meaning that there is this element of the one forms of this gamma that will allow you to retrieve the exterior derivative D, the differential, by taking the bracket, by looking theta times A minus A times theta. As you immediately realize, this is like totally wrong for the exterior derivative, because exterior derivative, if you do theta bracket A, that's going to be 0 for sure, because there is commutativity. So I'm trying to tell you that for a commutative algebra, you have that any module is a bimodule automatically, but left and right structure coincide. Here they do not. If you multiply from the left, it's not the same as you multiply from the right. So there is an emergence of a non-commutativity that the people in machine learning are certainly not aware, but also the people outside the non-commutative geometry are not so familiar with. Physicists, they do know because they exploit it all the time. But mathematicians working in homology, cohomology, they don't know this point of view. And I think that is quite fruitful, because instead of reinventing the wheel, what you can do is look what the physicists do and try to see if their construction makes sense. And indeed it does, as we will see in just a moment. So what we did with my collaborators is that, okay, they're interested in graphs that just have one edge per pair of vertices. What we can do is that we can do the calculus on an étale cover, and then we can, define differential calculus also for graphs that have multi-edge. Why not? And that's what we do in our paper. This is an exercise. We take the recipe and we do this. I don't want to, I just wanted to show these slides to tell you what you can do. And then what you can do, of course, once you have this machinery, you can talk about vector bundles. weak parallel transport, and you just parallel transport. You can transfer all this beautiful machinery that you have for the non-commutative geometers and the physicists using this theory to this framework of machine learning. So you translate and what is parallel transport is just a collection of linear map that moves from one vertex. So you have a vector bundle, meaning that you have this um, vector space attached to each vertex, and you think about parallel transport when you can move from one vertex to the other. Now you start seeing the important parallelism between this and what the machine learning people need, right? Because the machine learning people have a node, a vertex, which is, for example, a person like myself, which is assigned a vector space. The vector space assigned to this vertex may be all the features I have, my age, my preferences, my height, my health conditions, and so on. And clearly, if I'm connected to another vertex, I may share with the other vertex many of my features, right? So the friend, perhaps a friend is more likely to be a woman. This type of similarities between me and my neighborhood friend. Unfortunately, with the way they do it in machine learning, they have this parallel transport. They will transport information only when it is similar somehow. While with the shift neural network that I'm going to present in a moment, you are capable of capturing the information in a quite vast neighborhood so that you can infer predictions also on the feature of nodes, on the labels of nodes that are far from the node you are looking at. So that is the power. Yes, Hong, you have question?
Yes, yes. So Rita, so of course,
Yes.
I understand you also show on your slides that you work only on the graph neural network, but actually I know and could be considered as expert on the traditional and Bayesian neural network, but I do not work on the graph neural network. So so I don't know that each kind of the model for incomplete information used on the not or on the how to say edges.
Yes.
Yeah, and then how till now what I see is your how to say extending classical and continuous mathematics on graph. That is, of course, that's also interesting. But there is completely deterministic one. No.
Yes. Correct. Correct. We are sorry. I understand that you may have interest in more probability, but the way I'm doing it now is totally deterministic. You are correct.
Yeah.
But I'm
So
following what they do. It's not my idea. That's what they do.
so that you completely how to say try extend classical considered mathematics to the graph, and you then discuss how to say probabilistic aspect.
I personally do not, but my PhD student, she's graduating now. She will do graph probabilistic models. So she's expert in that. So she will be doing her postdoc doing that. So I can put in contact with her. She'll be very interested in exploring that direction. But you are correct. This is an important research direction that needs to be explored. I totally agree.
Yeah. Okay. So yeah.
Yes.
So
So
that
probabilistic
meaning
graph
at the
models.
moment there no learning because the learning that
No, I'm
right.
sorry. I take the fully deterministic, but you are right. There are something called probabilistic graph models. They're very hot, and she's doing them. And I will put in contact with her because
Okay.
I'm not, I didn't want to pursue this line of research with her because I feel that, when you're doing your PhD, you better be focused on, just graph neural
Yes.
network because,
So that we
but
had a lot of time, so it took later. Yeah. Thank you.
yes, but no, of course, of course. But I will make sure that you meet with her. Yes. Okay. So notice that you have something that in our paper, we separate the notion of weak parallel transport with the notion of parallel transport. think that in machine learning they don't really do. So they think that if they can go from U to V, they can come back. But we think it is very important that you may have a situation where you go from one place to the other, but you cannot come back because this will give to the geometry more interest. Okay, that is one point.
Sorry, may I ask
And
you? I am
yes,
lost regarding the parallel transport in a sense. I would
yes,
like to ask you what is E prime in the
yes.
definition?
Yes.
I don't
So
know.
the E prime is okay, it's wrong. Thank you for pointing
Oh,
out. There is a prime that should not be there.
okay.
So it's not that you don't understand, you caught a typo. I apologize about it. There is no
Nice
E
to know
prime.
that it is related, but it is the same, yeah. This
It
E
is the
prime.
same.
Okay,
You
thanks
go
for
from
sharing.
E
Okay,
to
yeah.
the to V, sorry, from U to V and you come back. Okay,
Mhm.
But
that is.
Thank you.
there
Of
might be many
Thanks.
edges, right? So
no. Right now we assume to have just one edge.
just one edge. Okay, Rita.
Yes, no, we plan to do it for multi-edge, but in our paper right now, for this part, we just have one edge. But we will
Okay.
do the multi-edge in the future. In fact, you see here we put the digraph less or equal to one means that we look at just that case. Okay.
Okay, Rita. Okay.
Yeah. No, absolutely. You are very right. Weak parallel transport you can define in general, but when you want the true parallel transport, you need to be able to go back and forth. Okay. Then you can define what a connection is. I don't have to explain it to you the importance. This was done by Brown and others, but they didn't do it quite the way we do it because what we've been doing with connections, we take the definition which is exactly as theirs. So it is the parallel transpose minus the identity. However, we are able to relate it with the non-commutative geometry point of view, because in non-commutative geometry, there is something called a non-commutative connection, and right or left, and we are able to show they are really the same, okay? In this case, we take a weak parallel transport, so meaning that you can take as many edges as you want, because you don't have this condition of coming back. That is makes it a bit tricky when you have multi-edge. And then I put down an observation saying that, hey, what we do actually mimics what happens in the continuous case. Because if you have a vector bundle and you want to consider parallel transport, that's a definition of connection given a parallel transport. And then you notice that is exactly what you would have in our case when you take your map R as your parallel transport, but the H is the unit because you think to move between vertex U and vertex V to move along an edge. Before you ask, we are fully aware that you could put a metric on the graph and instead of H, you can put some weight on the edges. And actually, that's actually very important in machine learning because some edges may be more important than others. But I will be basically hinting about it in the end of this talk and not now. But I'm saying that you can parallel many constructions. Okay. And here we come, the notion of curvature and together with the sheaves. And I put down this picture in the paper by Barbero, Bodnar, and big names into machine learning world. When they look at, they really have this picture. They look at the nodes. They put down this M, the manifold that mimics the the graph. And what is interesting, they're missing a crucial point that locally constant sheaves correspond classically to vector bundles with a flat connection. That we know. And this corresponds in machine learning to ask that you can always come back. So essentially, if you go from one vertex U to another vertex V and you are able to come back there with paying nothing, it means that your connection somehow it is flat. Is the holonomy idea, right? But that's like a severe restriction. They impose it, but it's severe. What you must do is to allow for if you do a loop, you shouldn't come back exactly where you started from. And this happens in Euclidean setting, not when you have some connection, some curvature, parallel transport. That's not what it is in geometry. So in our paper, we try to put this extra information, and we also been trying on a separate side of my research to make it concrete. So we're trying to look at concrete data set in this moment, in particular to data set coming from bone tissue, tissue that has tumor, tissue that doesn't have tumor, to show that actually if you look at this method with better eyes, geometric eyes, you can get better prediction. For the moment, it seems we are right, but the paper is still to be sent. So let's hope we are right in the concrete setting. Now, as I said at the end of the talk, because right, Hong, I'm towards the end, right? Is 1 hour. Am I correct?
You have a 15 minutes more, but you can, yeah.
Yes. So we're getting towards the end, so I try to convey, the last important information. So as I said, you can talk about quantum metric for quantum groups. That's again a very active area of research. And then something called a second order Laplacian, which, by the way, if you translate in all the language that we've been introducing, just an exercise, it turns out to be really the graph Laplacian. So these people in machine learning really use this graph Laplacian to transform information through the graph. So there is something called the heat equation, Fourier. So where you put suppose you are on it's an analogy. If you read my papers, it's way more than analogy. We prove stuff, but for the moment being, let's look at it as an analogy. So Fourier equation tells you that if you have a slab of metal and you put a source of heat in some point, then the heat will diffuse through time in the whole portion of the metal, in the whole metal disk, right? Same thing here. So if you put the information on a node, actually you do the other way around. So instead of diffusing the information, you are gathering the information from the neighboring nodes using the Laplacian. So these people claim it. In our paper, we prove it. Maybe they proved it and they forgot to put the proof in the paper. This is a possibility. I think that kind of they knew it. And so they wrote this Laplacian to diffuse information. But this way of diffusing information, first of all, is isotropic and in everywhere in all directions, which is not good because sometimes some nodes are linked by edges. There may be edges that diffuse very little information because for reason of your network. So first of all, you can put a metric to each edge that will tell you how strong is the information that you want to pass in both directions. And that's very simple to do. But then you also want to take into account other phenomenon in the graph. So you want to define what is called the connection Laplacian. So the connection Laplacian will have the connection built right into the notion of Laplacian. And this is defined by several people. There is the non-commutative people defining it. So if you give me a connection, okay, that for the machine learning people, it has a certain definition, but I don't want to go into the full definition, but it's really what you think. Then you can define the connection Laplacian when you have a metric, and you can write it in terms of parallel transport. Not very surprising. What is surprising to me is that you can do the same by looking at what the machine learning people do. Now, the difficulty is that they don't write a proof. They just write the algorithm. They just say, oh, we do this way. And you have to very painfully dig through their formulas to make things, what can I say, to put the little pieces of the puzzles together until you realize they're doing the same thing without knowing. Okay, so this is this is what the people, Bodnar, Barbero, and a lot of these big names do in 2022. They define the sheaf Laplacian, where they have an extra structure of a sheaf. And what we did in our work, we put everything together. So the theory of vector bundles, the theory of sheaf, the theory of non-connections in non-commutative geometry, in machine learning, and of sheaves all together to match them. And not surprisingly, we realized that the people in machine learning are looking only at a portion of what should be the full-fledged of an algorithm taking advantage. And that's what we've been doing. We've been trying to show these people that they have to be, more geometrical if they want the sheaves and the connection to truly help them. Because, I think we all know that connection, a flat connection, well, it's a nice object, but why do you need the theory of connections for it, right? It becomes interesting when there is curvature, when you have surprising stuff, not when you, otherwise, you don't need this beautiful theory. So they define what is sheaf, they define the sheaf Laplacian, and our theorem is something that we did together with my postdoc Zanchetta and collaborator Simonetti in 2025. So it is going online this month. We've been moving it. I don't know why. We have to do it to put it online. So if you have a bidirected graph, you have a vector bundle, you have a connection, you have a parallel transport, and then if you look at the non-commutative point of view, you build this nabla star nabla, you get exactly their machine learning. And so we put this bridge between the geometric deep learning sheaf Laplacian together with the quantum geometric one. So, and we showed furthermore that there is flat, while you can do better. So you can do curvature, you can do homology, cohomology, that they don't see, evidently. And of course, you can do it for semi-simplicial sets, higher dimension. Why not? You could do it. They don't, because they don't have a use for it, but of course you can. And what you gain if you do is more insight into the structure of your graph neural network. These are the references that, as I said, Bodnar, Di Giovanni, Brown, I mentioned. I forgot to mention the Barbero one, which is kind of important. Then there are my own references. And then there are the quantum geometry one. And I guess with the slides, with the 7 minutes, I end early my talk. Thank you very much for the attention.
Thank you very much, Rita. Yeah, for very interesting talk. Yes, so just a pupil also did kind of discrete geometry apply to graph theory, graph Laplacian. Can you compare your notion of the Laplacian? Is a graph Laplacian by, for example, Benkin and Yogi?
Excuse me, the usual graph Laplacian, you mean?
Yeah, so usually.
Of course. So if you look at the usual graph Laplacian, I put a proposition right here. It is the degree matrix. This is the diagonal matrix minus the adjacency matrix. Here we're talking about a very simple graph that has just at most one edge per vertex. It is unoriented, so if you wanted to look at it as a direct graph, you need to choose an orientation. And what you can show is that indeed this is a special case of Laplacian in a non-commutative setting, where you take the metric to be 1, and you give just an orientation. So up to a factor 2, but it doesn't matter, this is a constant. You need to give a constant metric, and then you need to give an orientation. But this orientation that you fix on the graph plays no role. This proposition is an exercise, but I think this is important exercise because we show that in our more fancy language, actually, in a special simple case, you get back, as you correctly are saying, because one thinks, wait a moment, but there is the usual graph Laplacian. What is this has to do with this theory? Yes, you retrieve it, of course, you retrieve it. So was it?
So, great, Rita, where is the proven this proposition? In which
It
paper?
is. I promise. I've been promising this paper by a year or two. Every time we look at it, we find some stupid detail to be fixed, and we don't want to put it out with some stupid sign error.
So,
but it's there. You know, you have to trust me. I want to publish it by February, so it will be out by February. I swear to God, this time is true.
send me that we should cite the EU reason in our book.
It is in your book. This part I'm sure. This is like a little calculation. I'm sure it is in a book, of course. Yes.
By means that I can cite your make that your reason.
Yes, I could cite your book. Yes, yes. But we did it also because it's not a big calculation. Yes.
Yeah. Okay. Thanks. Yes, that's really interesting. Is there some more questions? So, if there are no more questions, let us thank the speaker again. Yeah.
No, thank you. Thank you.
Yeah,
Thank you
so
very
we
much.
should have a lot of the discussion after. Yes, I am waiting for this. Your reason, of course, that is not my main interest, but that should be. I found it's very interesting, and you know that you can use and many people working on the graph try to find different version of the Ricci curvature, and there are many versions.
Yes, we do. We do. Yes, we have everything. But today I wanted to keep it, I don't want to say elementary because we talk about many things, but I didn't want to overwhelm the people with a lot of, calculations and detail. But of course, we have everything, the curvature, all the formulas, of course. Yes, yes.
So there are at least two different versions of Ricci curvature on the graph. And your has some more general concept connected.
Okay, so yes, this is a very, as always, you're asking a very deep question. So the curvature is linked to the two form. So what you need to do, you need to go to higher differential form. So you need to construct, instead of first order differential calculus, second order, third order, and so on. But then not only this, but you have to look in the graph of what is called the click, the tree click. So you have to tell me whether or not you are allowed to go around, right? Because you would have to link it to the holonomy. So if you always can come back and get the same thing, you have no curvature. But if you do around and you don't get the same thing, then you get curvature. And this is exactly the formulas for curvature. Yeah. This was the partial work I did
also agree with a different classical formula for curvature. Did you test?
So the way we did it, we agree with what the Dimakis and Brown have written it. We agree with them. I am not aware on graphs. There are different formulas. So if you have these formulas, please send them to me. I will be happy to code them.
Okay, I also not so interested in such a very discrete, but I was on different seminars, so I know there. Jürgen Yost is an expert, yeah, because he defined some version and I know there are another version, so I know that at least there are two versions of the definition of Ricci curvature.
I don't know.
So also I got your reason I should check, yeah. And then it's a classical one. Okay, thank you. And then if there are no more questions, then we really stop today and stop recording.